Okay, so let's go for it. Okay, welcome back to LispNYC. I'm your host, Arthur Smiles. I'm very excited for tonight because tonight we have two lists in one live stream. So remember to hit those thumbs up, share the video, and of course subscribe. You can always see our stuff at lisp.nyc. And with that, I'm going to get started. First up is Luther Johnson. He last spoke with us in 2019, where he showed up his very new project, MakerLisp, which is both hardware and a software implementation of Lisp. And now he's going to be telling us what's been going on since then. So I'm very excited to see Luther. And with that, let's welcome Luther Johnson.
Hi. So MakerLisp is an implementation of Lisp, but it is also the system software that is running on this little tiny CPU card, which is exactly the same size as a business card. And
Luther, your video is mute.
Oh. It shows that it's on here.
Oh, okay, yeah. It just might forget it. It's my browser.
Okay,
you're good.
So this is the CPU card. I've got a little SD card here.
Luther, I can't see you also, and if it's only me, then it's no problem.
Yeah, you can always reset your browser. I can't, but you guys can.
So do I need to do anything, or am I good?
No, you're good. You're good.
Okay.
Let's continue. I can see your
I'll continue.
How do you reset the browser?
You can just hit refresh, and you'll just log out and log back in.
Okay, thank you.
Yep.
But if you can put the card a little bit more in the middle of the screen. Oh. Yeah, that's it. That's it.
Okay, so this little CPU card, we have a microprocessor here, have some SRAM, we have a battery for a real-time clock, we have an SD card, we have a USB UART connection, and this is a little self-contained computer, and I can show demos of this later on in the meeting. I won't do that right at the moment. But it can be a self-contained computer all by itself, but there is also a motherboard that you can plug in this high-density connector. On the back of the card is a high-density connector, and it can plug into this I/O expansion board. And you can see I've got a breadboard here where I can do little experiments, and I've got a SPI and I2C devices here. And so it's a complete little educational experimenting kind of thing. So it can be a personal computer, or it can be like an electronics playground. And so I'm kind of doing the Arduino thing, right? But I wanted a better programming environment than Arduino. And I wanted to program at a low level to the machine in Lisp, because Lisp is a simple language and it's kind of all encompassing and functionally complete, and there's just about nothing you can't do. But there's no operating system. The Lisp is running in ROM on that CPU card. It's a conventional CPU. It's a Zilog EZ80, which I'll talk more about later, but it just happens to be a kind of a microcontroller that also has access to large amounts of memory, which is good for Lisp. And it turned out to be just a convenient processor to use for this card. So the whole idea was, let's do the embedded control, Arduino, experimenting, playing with Maker kinds of things, but let's do it in Lisp instead of the Arduino language, which is kind of like C++, but kind of not. And so that's the whole thrust of the project and that kind of thing. But in the process of doing it, all sorts of interesting things were discovered. So Arthur, I'm going to try to share my screen right now, if that's okay.
Yep, that's fine.
and is that going? There we go. Do you see it?
Yep.
So here I've got my website up, and it's MakerLisp.com. And, this is kind of the front page. And then I also made a ventilator in 2020 and 2021. And there's a link through to that site if you're interested, but I'm not going to talk about that today. And, news, latest developments and things like that. But on the download page, you can get to more information about the project. There are release notes here, and there's a little bit of a hardware reference manual, but the source archive is here, and you can download all the software. And, I keep publishing new versions of that periodically. So that's the project. Let me go back to the other page. Besides, that's the CPU card, but this little picture, you can see that I have a little stand here with a 40% profile keyboard, and you can see the experimenting board and the whole system there. So that's kind of like, that's the basic idea. And so now I'm just going to highlight a couple of the features of the MakerLisp Lisp implementation and the system in general. And I'm going to do that by hitting some slides in a previous presentation. And then I'm going to switch to a presentation that has the most recent developments.
Yeah, before you do that, I actually saw someone raise their hand. I think it was Robert.
Okay.
Do you have a question, Robert? Or was that like a false alarm? Okay, maybe it was a false alarm. Anyways, yeah, go ahead, continue.
Okay.
I might be interrupting you if we get any questions from YouTube.
Sure. So I'm going to just kind of race through a few of these slides and focus on the things that are just most characteristic about the differences of this Lisp. So this is a little bit of the rationale, and anybody who's interested, it's my email address is luther@makerlisp.com. Send me questions, and I can send you these presentations or anything else. I'll just go into a little bit of the details of MakerLisp. Underneath, in the implementation, is an SECD machine. That is kind of the virtual machine on which the whole system is based. And that's, stack, environment, controller, command, and dump, if you're familiar with that. The whole implementation is written in portable standard C, like C89C, very, very vanilla C. And of course, the higher level forms are written in Lisp itself. So it is not any particular dialect that is recognizable as a standard anywhere else. It's a blend of Common Lisp scheme, and of course I have a standard C library, so you have those functions as well. I picked what I picked because I just was making a system that I liked, and I wanted to be small and compact. I like the scheme evaluation model, so the scheme runtime model is everywhere in the way the thing really works, but the functions and the primitives are with Common Lisp or traditional Mac Lisp. And when I say Mac, I don't mean Macintosh, I mean Project Mac, like the original Lisp. Spelling and semantics and defaults. So, car of nil is nil, car of nil is not throw an error, for example. And I have set Q, I don't have set bang, and those kinds of things. So, but it's very recognizable. You look at it, it looks like ordinary Lisp, and it works pretty much like ordinary Lisp. But underneath, it is scheme, runtime semantics, there's one namespace, there's closures, there's continuations, there's tail call optimization, there's all that stuff. The machine itself, I won't go into a lot of details until later when I talk about some new things. You can ask me questions about various different aspects of the language later. It's got a few things that are a little different to choices I made, but not important right now for this level of the talk. It does have Common Lisp style low-level macros. And so, you know, with macros and closures and, you know, continuations and backquote, I mean, you've basically got the full deal of everything you need to extend the language. It does work as a JITted system, just in time, compile on the fly kind of thing. And it breaks apart the Lisp, the Lisp language forms and breaks them into virtual machine instructions that are based on this SCCD machine. I'm not going to go through all this right now. It does have kind of an interesting garbage collector that helps with you know, runtime performance. We can get into that later if you'd like to know the details. At this point, I'm going to flip to the other presentation and just talk about, so that was the state of the system 2 or 3 years ago. And I'll just talk about what I've been doing recently.
Great. Before you do that, I just want to mention for people that are on the live stream as well as here, is that we actually have the entire talk that he gave in 2019 on our YouTube channel, where he does go into amazing detail on all these subjects that he elided over. So after this talk, if you guys want to check that out, you can check that out. It's a great talk. And also Luther was actually there when we premiered it. So there's some commentary on the video by Luther himself. So
yeah, I mean,
definitely worthwhile checking out, even if you've been there.
At one point, I forgot, you know, what a particular data structure was doing in the implementation, but you know, like right after the talk, I remembered. So when we did the preview, I put the information back in. So let's go to this. And what have I been doing recently? Well, you know, kind of just taking care of business in a lot of ways. All of the boards, you know, in the system, there is the CPU card, but I've also got a VGA card and a keyboard controller. And I've also developed a number of little temperature sensor devices that work on either SPI or I2C, just so that you could have things to experiment with and do your, you know, your low-level communications. So the CPU card's been spun 3 times, and the VGA and keyboard controllers have been spun 3 times. And what I did is really not change any functionality, but just kind of cleaning up the layout and some quality issues. And also sometimes I had to change parts because parts were not available. And, you know, voltage regulators, I had a stock of voltage regulators, then the place that does my boards for me lost them. And so I had to kind of change bill of materials a few times, and I had to change things. But the other thing that happened was, I kind of got more and more control over doing all parts of the process myself. PCB printed circuit board respins, developed more fully the SPI and I2C support, and some demos and some add-on boards that you can use. I did a fair amount of performance work, kind of doubled the performance. I made some changes to the evaluation model, which covered certain corner cases in a nicer way. And several people asked me for functions or utilities, or hey, can we do set Q in pairs of variables and values like in Common Lisp? And I added those kinds of things. So if you want something, just ask, I'll probably put it in. And then the last thing is because of the shortage of chips and the fact that no one can buy anything anymore, I wound up in a position where I couldn't get the processors I needed, and I couldn't get any other reasonable replacements, so I'm making my own. So again, with the board respins, issues of, I changed design tools. The previous, I had two different engineers who did hardware designs for me, and one of them had worked in Eagle and the other one had worked in DipTrace. And and gradually, I sort of designed things with them at kind of a schematic level, but I kind of counted on them to do the modern day, manufacturing stuff. But gradually over time, I learned from them how to do everything myself. And I switched everything to one tool set. And so now all the boards are all, the design data has all been moved to one tool set that I have, and I've respun the boards myself. So
that's cool.
Learning how to do more of it myself, and also cleaning up like the hundreds of small, I wish that was over there, and those kinds of things. And just made the things nicer, more manufacturable, cheaper, more reliable, all those kinds of things. And then the SD card power, I had a little circuit in there to turn it on and off, and that was amazingly troublesome over the years. And at every level of implementation, I came up with some workaround so that the products that you actually received worked properly, but I never really liked the way the circuit was working. And I kind of got there in 2 or 3 steps to the final version that I like a lot now. And so that was, it's funny how little things like that can be amazingly difficult and it's an involved, something so simple as just kind of like turning on and off power with a particular kind of device. And, because these SD cards, they have little ARM processors on the inside. So there's a lot of stuff going on in there, and they can kind of trip you up. But anyhow, those kinds of things. So basically quality and control of the boards. I really beefed up the SPI and I2C support, and I developed some temperature sensor boards, which when we go back to the live camera, I'll show you a couple of them. And a demo with a 7-segment clock display. All these things just demonstrate how the system works. But in the process of using Lisp at a low level directly to the machine to do these kinds of things, some opportunities for the language development and optimization came up. And so I did that, and I'll talk about that in a moment. So one of the things that came up is when you're doing a lot of I/O to devices that have a base address, and then they've got registers at different offsets, you wind up with a lot of constant expressions in your code, right? And so it's nice to fold those out and reduce those as much as possible. And although this was a kind of on-the-fly JIT, compile on the fly to virtual machine code kind of thing, it didn't have a lot of optimization in it. But this was an opportunity when you have lots of integer expressions, that are constant, you can, and some of these things just kind of would go away by themselves by the nature of the execution. But some of them I had to kind of work a little bit to gather or to order in the proper way so that they'd all show up at once so I could collapse them. And so I did that. And it's both a space savings, it's a little bit of a performance advantage, but when you're dealing with I/O devices, that's not really the main thing, but it's a big space savings, it just makes your code smaller. Also, a similar kind of thing, doing simple operations with a constant. I added a virtual machine primitive for that and folded that out. The most common low-level virtual machine routines everything was in C, but I took the 9 or 10 that were really happening a lot, and I recoded them in EZ80, and the CPU is a Zilog EZ80, assembly language, and that kind of doubled the performance of those routines. And so everything together, the overall performance improved by about a factor of 2. I have a little demo program called the tac yochi function, and the program's called bench tac, and that doubled in performance. So you're not going to see a 2x improvement in your everyday feel of the product, but if you've got anything that was computation intensive, of course, then you would notice. Another thing that showed up was the idea of a specialized lambda. So briefly, normally when you have an anonymous function, a lambda, every time you create a new anonymous, a new, lambda, a new function, a new applicable object with the lambda construct, what changes in that object is the environment that is attached, but the code doesn't change, it's shared. And that's a good thing most of the time, because then you don't go through the rejitting every time you hit the same code in the text, even though it's a new, unique lambda because you're applying it from a different environment. That's a good thing, and that makes it fast, and you benefit from the accumulated performance advantage of already jitted code. But then sometimes you would like to have independent lambda functions because you'd like to specialize them and make special versions. And so with this SPI and I2C things, what I did is I created an object for controllers of SPI devices on particular pins, on particular places. And then I had macros that were underneath that did the things, but I specialized them because I would define constants and then pass them in to the objects that were created. And when this object was created, it took that constant definition, and then that was expressed through macros, and then the macros landed inside some of these functions. And because now the lambdas in an S lambda, specialized lambda, the body, the code is not shared. It's independent. So if you then specialize it, it only affects that one. And for that, in that way, I could make very efficient I/O device objects that were specialized by the pins and the particular rates and things like that that were specified when the object was created. So that was just an opportunity that presented itself, but it's kind of a generally useful feature, I think. Another one, I don't want to get into too much detail here, but one of the features of MakerLisp is that you can pass not only primitive functions and closures or lambdas as applicable objects bound to arguments, but you can pass macros too. And in fact, everything in the system, you really shouldn't have to think about whether it's a macro or not. A macro or a lambda or a primitive function. You just pass it and use it, and it'll work. But macros present a particular challenge. And if you're not careful, the JIT can get too aggressive, and the first macro that you pass in will then contaminate the code that it landed in that applied the thing. So there was something I was doing to prevent against that, but I never really liked it very much. I didn't like the way I was doing it, and it also presented a performance deficit when you were just passing ordinary functions. So I fixed that, and it's kind of involved, and so you can ask me questions about it later. But I did it just about right, and so it presents no excess overhead to functions or primitives, but if you pass a macro, it will get evaluated in such a way that it won't, for the rest of time, contaminate the site at which it was applied, but it'll only do anything extra in the case that what you applied was, on this particular invocation was a macro. So it's safe, but it's also the least performance deficit. I did a couple of things to make internal defines a little bit more flexible. You can pretty much have internal defines anywhere in your function and inside of conditionals, and you won't have a problem. It'll find the right thing, and it does it efficiently. In the earliest implementations, you could actually make up a function by taking other functions apart and putting them back together and kind of like cobbling the pieces together with cons and various things yourself. You can't do that anymore. The system can tell whether or not you've cobbled something together or whether it was actually created through a define or a lambda, in the right way. So that's just a safety feature. And it just turned out, and I kind of did this on purpose, that I was like delaying the incrementing of the release count until 1.5 was the one that I wanted to stick with, because Lisp 1.5. So that's kind of what happened there. Okay, last couple of things, and then I'm done with my talk. I only have 20 EZ80s left, and I can't get new ones until the end of the year, and every other microprocessor that I might consider replacing it with also is in the same boat. So I just undertook, late last year to start making a processor on my own. And the FPGAs that I'm using from Lattice, they're about the same price as the EZ80. So I should be able to get what I want, and it'll actually be a little bit better. So the EZ80 was like a Z80, but the EZ80 has a big flat 24-bit address mode without any segmentation or paging or anything like that, a nice big flat address space. And that's the way I was using it. So I wasn't really using the Z80 compatibility, although you can run CPM on this system if you want to. I've got a CPM port, and there's a demo in the system that I ship. But I was using the EZ80 in its big flat mode, and it ran at 50 megahertz, which supported fast zero wait state SRAMs running at 50 megahertz, but internally it's 50 megahertz as well. This processor I'm making will run at 150 megahertz internally. The memory interface will still be at 50 megahertz, but everything will be running at 3 times the speed. So when it's not talking to memory, things will get done faster. It's a lot of work, but I'm making progress. And, by the end of the year, I'll probably have it. But before I can get new EZ80s again, I think I'll have a replacement running in this FPGA. And then I'll just switch to that. And it's in the same package as the EZ80 processor, and I'll have to relay out the board again, but I think I'll have my solution. Of course, it needs a C compiler as well. And
I have a question about that. So are you
Sure.
saying that the new boards will have a FPGA
yeah,
processor? Okay.
yeah, you won't be able to tell the difference. It'll look exactly the same. Instead of saying Zilog, it'll say Lattice, but
Mm-hmm.
and it's the same pin out.
Would it be possible to reflash it? Let's say you had here's an updated model of the machine, right?
Absolutely, it is.
Oh, that's really cool.
No, it's just the same way that you can reflash the software, and I've got an update utility, and all that kind of stuff. You'll also not only be able to reflash the software, but you will be able to reflash the FPGA. So I'll build boards like this, and there will be bugs, and I'll fix the bugs, and I'll send you updates, and you'll be able to update them.
That's awesome.
No, yeah, why not? I mean, that's what FPGAs are for. So,
but I just like the idea of you have something that works, but then if you want, for people that get this thing, I mean, this is really ultimate maker, right? Where you can be like, you know what, I'm gonna try this experiment on your processor and change it a little bit.
You can. I mean, I'll open up everything, and just like I had before, and you will just like before. If you want to just change the ROM software within MakerLisp, I've got a little software utility that does, and you do upgrades that way. But if you're going to want to change the FPGA structure, you'll need the I/O expansion card. And by the way, all the other boards will still work exactly the same. And the I/O expansion card, the pins that previously went through to the EZ80 programming stuff will now go through to the Lattice programming stuff. But you should be able to do everything. You might have to buy a little pod module or something like that. I'm not quite sure about all that yet. But it won't be completely.
Potential is exciting. I think
yeah, but I think you'll be able to do it with the I/O expansion card, and you might have to buy a cable from Lattice. I've got several of them here, and I'll show you one in a moment. So you'll probably have to buy just the same way. Like if you wanted to really.
Yeah, if you're going to show it, you're going to have to hit the your start stop camera. Hopefully it'll work.
Well, yeah, that's fine. Hold on a moment. So I'll just finish with the C compiler.
Okay.
The C compiler is a version of the original C compiler from Bell Labs from Steve Johnson. And, the first C compiler was done by Dennis Ritchie, and then Steve Johnson, working in the same lab like down the hall from Dennis Ritchie, and they worked together a lot. Was meant to be a little bit more portable and a little easier to port to other machines, and it was, but it's not quite as portable as the way we think of things today, but it is portable. And the thing is, the first two C compilers are not like any compilers before or since. They really are interesting, and they take a very different approach. I mean, it is a classic approach that's documented in the Dragon book, Alfred Aho, and it is kind of like some techniques that were well known at the time, but have been kind of forgotten. And modern compilers have moved in a certain direction that have it's sort of like RISC machines and compilers moved in a certain direction by themselves. But the machines that we had in the mid to late 70s and early 80s, and the compilers we had at the time, they were matched. And they did different things that were more appropriate for those kinds of things. Well, the processor I'm using right now and the processor I'm making now has more in common with processors of the late 70s and early 80s than modern RISC machines. And the compiler techniques from back then are also most appropriate. So I'm going to leave it there and not get into too many details, but I'm having fun and making good progress. The C compiler is about halfway done, and I'm pretty confident that I'm doing the right thing for this processor. But the last line on the slide is kind of like similar to something I said in my earlier presentation about the project in general. It's like I kind of conspire to make everything fit together. And so the C compiler that I'm working with is just right for this processor, partly because I'm making the processor that's just right for this compiler. So, it's sort of like that sometimes compilers have difficulties with features of machines, but what if you design the machine to be just perfect for that compiler? And so I'm doing both of them at the same time, and they're working out and they're getting along. And it's kind of it's a fun thing. So if you saw any elements of that style of design in the project in general, well, I'm up to my same old tricks. And so that's what I'm doing with the C compiler and I'm calling the thing Core 24. So somebody I was talking to said I should call it COR for C optimized RISC. But anyhow, that's what I'm doing. And
it does 24 stand for, because it's still 24-bit?
It's a 24-bit processor still.
Okay.
Yeah. And I'm going to stop sharing. And now I'm back. And I guess we'll move on to the next presentation.
Yeah. Does anyone have any further questions? We will also have Luther afterwards if people think of stuff or they want to see some more demoing.
Yeah, not exactly a question, but it reminds me a lot of Precursor, if you've heard of that. It's also like FPGA based.
No, what is it? Tell me a little bit more about it.
The idea is that it's end-to-end open source hardware and
Mm-hmm.
as well as end user verifiable. So everything is it's like low tech or like physically big enough that you can actually inspect it, and then the CPU itself is implemented in code,
Mm-hmm.
and then flashed onto the FPGA.
I see. Yeah, I mean, I'm designing in Verilog, and everything will be available. In the project so far, I've put the schematics out in the bill of materials. I haven't put the manufacturing data up, but you can pretty much figure it all out. I mean, if anybody wants my dip trace data, I'm happy to give it to them. It's not a big deal. Although I don't promise to like answer questions about details of the dip trace and the manufacturing data. I reserve the right to change that anytime I want to, but for new boards. But anybody wants it, they can have it.
Cool.
That's awesome. Yeah, so if we don't have any more questions, we'll go to our next speaker. Our next one is the one who just asked that question, Oliver. And Oliver is going to be going over. Oliver is the one who introduced me to ChiaLisp. So now I'm very excited for him to introduce us to his version of ChiaLisp that he's developing in Swift. So with that, Oliver, you got the floor.
Cool. Thanks for the intro. Let me share my screen. Cool. So technically, I haven't implemented ChiaLisp. ChiaLisp is the higher level language that gets compiled down to CLVM. So what I've done is a CLVM implementation.
Okay.
And it's pretty much a straight like transliteration of the Python implementation. So I've really just been like working through the code and just trying to implement it in Swift. I'm not trying to like rewrite it or anything, but it's mostly working, which is pretty cool. I was thinking I would just walk through the code in like a somewhat logical order, highlight any interesting stuff, and yeah, I'm really just looking for feedback because I don't have much experience with Lisp. So yeah, any comments or feedback would be much appreciated.
I just have one question. Can you give a brief overview of what is the ChiaLisp dialect?
Yes, good idea. So this is the repo, Chia Network, CLVM. There's a really good docs site which covers everything. I guess it's fairly it's as minimal as possible. They really stripped everything but the essentials out. So like I can give you some example. I can show you some example code. Or this is not the best example code to show you. Let me try to find something a bit simpler. If you give me one sec. Okay. So this is an example. So the whole context of this is in a blockchain thing. So, but it's not specific for that. It's a generic language. So in this case, this is a puzzle or a program that locks a coin with a password. Hopefully this is not. I'm not sure what's Lisp and what's ChiaLisp, so I'll just explain everything. Hopefully it's not too basic for you guys. But so mod stands for module. It's like kind of like a function, and it takes in 3 arguments: password, new plus hash, or like the new address of the coin, and an amount. And then basically it checks if the password is equal to this hash or the hash of the password is equal to this hash that we've baked into the puzzle. And if it is, then we create a new coin at that new address with the amount specified. Otherwise, we throw an exception. So it's pretty standard Lisp, I believe. There's a page with all the operators I'm trying to find. Okay, maybe there's not a great. Oh yeah, here we go. So pretty standard operators, basic math stuff, string operations. There's a few more advanced things like hashing, some stuff to do with BLS signatures, which is the signature scheme they use. But that's really about it. I could give you a little. We can run it from the command line. This is the Python implementation I'm running, but we can do like something like quote hello. Oops. So that'll output hello world. We can do something like add 3 and 5. It should work. Oh. So what's going on here is the 3 and 5 get interpreted as numbers of the arguments. So we want to pass. Yeah, this is getting a little bit into the weeds, but basically the arguments are numbered, have an interesting numbering.
I'm wondering why you're having a dotted pair there.
You can sometimes leave it out, but I know I'm just doing it for safety. But yeah, basically the arguments are the numbering is it's like the traversal of the tree. So 2 refers to the first argument, 5 refers to the second one, if I'm remembering correctly. I'm guessing not remembering correctly. Yeah, I'll just copy the example. So you can just quote the numbers directly. So yeah, that's just a quick intro. I hope that kind of answers your question. I don't know if there's something specific you were.
Oh yeah, I was wondering why this Q, what the Q there is for.
So Q is like quote. So it just prevents it from being interpreted as an argument number.
It's just a different syntax instead of putting a quote there.
One thing about ChiaLisp is the syntax is very terse.
Yes.
And its primary design, what makes it really unique is its primary design goal is to run as a this CLVM is sort of equivalent to the like in Bitcoin there when you're doing a Bitcoin running a Bitcoin block, it's actually a little program, and this is a similar idea to that. So or like in Ethereum, right? So it's really designed to be run, in a distributed manner. So everything is designed to only work within a certain space of the programs that you send in, and that kind of thing. And for more details about this, we actually had the talk on this particular subject in September, and the link is in the link is also in the description of this live stream. So if people want to check that out after the talk, they can check this out to get into the details, including like an over an hour demo of everything that he's showing here from the creators of this.
Cool. Hopefully that answers it. Anything else you wanted me to go over before I dig?
No, that gives me a flavor. Thanks.
Cool, no problem. So yeah, I was thinking, just walking through the code. If anybody sees anything they're interested in, I can spend some time on that. So feel free to interrupt me.
But yeah, one thing I recommend is just to make the code bigger.
Oh, yep, good idea. How is this better?
Is everyone agree? Is it good?
Do one more to be safe.
Yeah, I think I can see it pretty good.
Cool. So basically, everything in CLVM is either an atom or a pair. I assume you guys are familiar with those terms.
Yep.
Mhm.
Cool. Atom's just like some bytes, and pair is a pair. So I've defined. Let me just pull up the original code on the side. That might be interesting. So there's a bit of hackery to get everything working in Swift. It's not quite as clean as Python, just because its types are a little stricter and it's not quite as flexible. So it's, yeah, I've defined a protocol, and then I've created this class CLVM object, which conforms to that protocol. Again, it just has an atom and a pair, and just an init method, which takes in a castable type. I'll get into that in a second. And then basically, based on the type that we pass in, we just fill in pair, the atom. So castable type is one of either sexp. How do you pronounce that? S expression?
Yeah.
Okay, it's a X
Sex
expression.
P, that's how I pronounce it. I think it's pretty sex P.
Sexp, so that would just be straight conversion object, byte, string, int. G1 is like the BLS signature. I believe it's the public key or the private key. I forget which. Or list or tuple. I had to do this weird indirect case thing because it's a recursive type. So this was the only way I could get it working in Swift. But I thought that was actually pretty cool.
For people that aren't familiar with Swift, like myself, what is indirect?
Well, it throws an error if I don't have indirect here. So indirect basically just allows you to reference the type, the containing type. So you see there's the enum. In this case, the list is like an array of castable types. And since the enum itself is a castable type, we have to add indirect to support that. Otherwise, the compiler will complain. So that's CLVM object. And then we have a sexp, which is a simple wrapper on top of.
Does that stand for S expression?
It does, yeah. We have S expression, which is basically like a higher level API on top of CLVM object. So it's still just an atom and a pair, but it gives us a few other methods to interact with it. So for example, the main one is basically just like we can compare two S expressions, which uses like a stack-based comparison. We can iterate over all the values in the tree. What else? First and rest operators, cons. This is like a static method, so we can take any castable type and then convert it into an S expression. So yeah, this is the higher level API we use.
So I have a question that I wanted to ask you. Is there a I think is there a particular use case that you see in implementing this in Swift? Are you planning on using this on like Apple devices or something?
Yes, exactly. This is part of a larger project, which is an iOS/Mac app, and yeah, Swift seemed like a little easier than trying to get Python working and cross-compatible with Swift. I was thinking about using the Rust implementation and trying to bridge that, but I figured it's fairly straightforward. There's not too much going on, so I thought it'd be a good learning experience. Just do it myself.
That's great.
Yeah, so really just some helper functions here. We have like converting a castable type into an S expression. It's not super interesting, but yeah, I'll continue on unless you feel free to interrupt. So here are all the operators. These are like quote, that's what we were just using, apply, I believe it's if. And then we have like some more advanced operators, math operators. That's pretty much everything. So we define like a dictionary keyword to Atom, which is basically just the human readable operator into the code, the raw value that gets interpreted. Just some convenience, like rewrites of, yeah, self-explanatory. Here, okay, I'm just gonna zoom out a little bit just because it's getting a little big. And then, yeah, so we have this operator dict. The Python implementation is actually like just a subclass of a dictionary. So the point is to have this call method, which allows like dynamic operators to be added. Swift, that was a little trickier to do in Swift. Yeah, so
What was the sticking point that you had the hardest time with making a dictionary in Swift?
I don't quite remember. I believe this call thing is a Python specific thing. I just remember it being hard to subclass in exactly the same way that it did it. So I just kept the same functionality, but exposed it through an actual class instead of subclassing dictionary. So I still have this call method, but instead of just being a dictionary itself, I keep like a map of data to S expression, basically, or a map of operators internally. So when we call oh yeah, sorry. When I overrode subscript, so, or maybe, sorry, I'm getting a little lost. But yeah, it's the same functionality, but with a class instead of a dictionary.
I see. Okay, cool. Thanks.
Yeah, sure, no problem. Yeah, so nothing too interesting going on here. This is where the actual operators are implemented, like all the core ops, if, cons, pretty basic stuff. Like for example, if we arguments, that, in this case, if takes exactly 3 arguments. And then we literally just check if like the first argument is null, and if it is null, then we return the second or the third argument. Otherwise, we return the second argument. So it's like if x, y, or z, yeah, equal. Yeah, I don't want to go too in depth into this. I figure it makes sense.
Yep,
so these are some of the more interesting operators. So like we have SHA-256. Same thing. We start hashing. We iterate through all the arguments. Like update the hash with that data, and we finalize that hash. Convert it back to S expression. Yeah.
So I have another question.
Mm-hmm.
If I remember from when we first talked about ChiaLisp, that ChiaLisp has ends up compiling down into bytes, right? Does this CLVM, does it read those programs so you can?
It does, yeah.
Oh, okay,
so,
cool.
I was going to get to that at the end, but I'll just jump ahead and come back. So
I'm willing to wait.
Okay, I'll get to the end. It's not super exciting, but I'll get there. Yeah, so we have all these other arguments or operators. Like a lot of the math stuff is in here. One thing to note is that we have this concept of costs. So each program is bounded by a max cost, and each argument or each operator has its own cost. You can see like some of the signature stuff has a very high cost, but like if is pretty low, for example. So when we run an operator, we return not only the result or what it evaluates to, but also the cost of running that operator. So that gets accumulated and tracked as we run the program. Okay, so we've made it to run program, which is the meat of everything. Takes a program, some arguments, this operator lookup dictionary we were just talking about, an optional max cost. I don't quite understand what pre-eval function is, to be honest, but I don't think it's too important. But basically, it's stack-based. So when we start up, we push eval onto the stack, and then we push the cons with the program and the arguments combined. And then basically just while the op stack has value, we'll pop the top operator, run that operator, keeping track of the total cost, and then throw an error if the cost exceeds our max cost, and then eventually just when the stack is empty, then we return the final value and the total cost of running that program. There's a couple of operators like built into this run program, or like private operators, I guess. So like eval, for example. Nothing too interesting, but I'll walk you through it anyway. So we pop the top value. If you remember, we pushed the program and the args onto the value stack down here. So we pop that off. We split out the program and the arguments. Sorry, and then we so if there's we want to evaluate from the bottom of the tree up, basically. So that's what this is doing. It'll evaluate all the arguments if necessary, and then eventually evaluated all the sub arguments and sorry, I'm getting a little lost here.
Yeah, that's all right. I'll let you get your bearings, but I got to say that eval is probably the most important thing that makes a Lisp a Lisp. So
Okay.
It's kind of great that you're you started out as really getting into Lisp from CLVM. So it's I think this is a great cross mixture of like how people get involved in things, right? And one of the things I was excited about having both you and Luther together is that you both are creating lists, right? And so we're seeing like the different approaches to it, right?
Yeah.
So this is like the totally opposite approach, because it's a much like Luther's designing a problem for like I want to build a board, right, to be able to make things with it, and I want a list that runs on that board. And CLVM is about we're doing like a distributed, in this case, a cryptocurrency. So we have a totally different mindset for a totally different problem than we've ever seen Lisp used for, really. So anyways, I'll let you continue.
Cool. That's really interesting. I didn't realize that eval was like the center of everything. So, but yeah, I'm curious to ask more later about like why that makes a Lisp Lisp.
It's basically writing Lisp in Lisp. Really, there's like this idea, the meta Lisp interpreter, where I think McCarthy went over. Okay, here's how you write Lisp in Lisp, basically. And Paul Graham described it as the Maxwell equations for programming. Because like when you see how Lisp is written in Lisp, it looks very simple. You know,
Right.
So yeah, eval is a key part of that, right? And macros and things like that are all built on top of that.
Got it. Yeah, so we don't have any macros or anything. This is literally just interpreting the bytes and evaluating them. But yeah, so I think I got my bearings. Basically, we split out the operator and the operands from our current value, and then we evaluate them. So we apply the current operator with the whatever values are on the stack, and then basically just evaluate them until we finish and there's no more operands, and then we return. So that's eval. Sorry, that's not the best walkthrough. I don't completely understand the like ins and outs of everything. I really just been working through the code and trying to get it working, and it does work. So
yeah, well, and that's why I thought this talk was important for people to know that you can approach things, and part of a lot of Lisp is like learning about it, in people in their various journeys, right? And you're journeying through this, so it's great to see like something in progress, so to speak.
For sure. Yeah, so just traverse path is the way we traverse a tree. So I actually have a few tests here. All right, never mind. I'm not going to get into that. But yeah, so that's run program. It just runs everything, and then one higher level is the generator, which is now this is like the blockchain specific thing. So it's a wrapper around run program, which runs the program and then checks the cost and stuff like that, and then at the end it converts everything into these conditions. Which are basically how the puzzles interact with the blockchain itself. So you can do things like I was saying, create coin. Yeah, you can create a coin, or you can like add assertions, like assert that my age is greater than X amount of seconds, or there's a number of things you can do. These are basically what you can output. Create coin, assert that a signature, something has been signed by a specific public key, various assertions like assert my amount. This is how you interact with the blockchain. So when the program itself has no concept of coin or any of the blockchain state, it can only output these conditions, which then get evaluated at a higher level outside of the Swift or the Lisps. Okay, we've made it to serialize, which will convert a S expression into some raw bytes. It's fairly simple encoding scheme. I forget the exact details, but Yeah, so like if it's, we basically, it's like a prefix and then we know how much to read. So for example, if it's a cons box, we prefix it with FF, like 255. Like we prefix 1 bytes up to, or yeah, 1 byte, you know, or yeah, basically just the size, and then we read that. So we, at the end, we have yeah, we have this S expression from stream, which takes in some data, and then outputs, returns an S expression. And in this case, it's similar to eval, but in this case, we are pushing this read S expression operator onto the op stack, and then we just recursively do that, basically. So we check if it's a cons box. If it is, then we handle that. Otherwise, we read an atom. And then, yeah, it's really just checking what the length is, making sure you're reading the right amount of bytes, and then just converting that back into an S expression.
So this can both serialize programs and deserialize them, right?
Yeah, the Python can. I'm not sure if I've needed the serialization part.
Okay.
Let me see. Oh yeah, no, I have. Yeah, so we can, same thing. This takes in S expression and returns some bytes. So in this case, we start with the stack of the S expression, pop it off. If pair, then we just, or sorry, if it is a pair, then we append that cons box marker, and then the left and right values. Otherwise, we'll recurse back into this, or go back into this atom to byte iterator. Yeah, which sets the correct length and everything. Yeah, and that's about it.
Awesome. I have a question. If people want to help you contribute to your code, is there a do you have the code publicly available?
Not yet. I really wanted to, but it's still it's intertwined with a couple other packages, and I just haven't been able to clean it up. And it's still a little difficult to use. But it will be up at my GitHub. It's just LispNYC.
Okay.
If anybody wants it in the meantime, I'm like happy to send them a copy of the repo.
Awesome. Okay, great. Yeah, keep me informed, and I'll post the link to it on this video. So if people see this video, they'll know where to go to. Awesome. Does anyone else have any questions?
I was wondering, so what's the overall application, and what are you going to use this system for?
Oh, well, I'm really implementing the Chia blockchain code, which is like the full node. So this runs everything that you need to connect to the network, you know, spend coins, have a wallet, all that sort of stuff. So I've implemented that in Swift, and the MV, like the minimum viable product, is a wallet that will work with Chia. But the real motivation for this is to develop like offline first apps for. I'm involved with NYC Mesh, which is like a community network in the city, and we really want, or like the vision has always been to not only connect people to the internet, and like servers elsewhere, but to have full apps running locally on the network, so we don't have to go out to the outer internet if we don't want to. And I figured Chia would be a really good base layer for these sort of apps, just because I've tried to do it in the past, and I've had difficulties with, since there's no central server to talk to, like knowing which is the source of truth, or for example, if we're doing like a chat app, knowing how to synchronize the ordering of the messages, that sort of stuff, it's pretty difficult. So I figured being able to use Chia not as so much for the financial aspects of it, but as a decentralized database, literally, would actually work really well. So that's how I ended up doing this. It really, I didn't intend for it to go so deep with it, but in order to do anything, you really need to interact with the chain itself. And in order to interact with the chain, you need to be able to run this CLVM, or in addition to many other things. But yeah, this was necessary. Yeah, does that answer your question?
Okay.
Yeah, I'll send you guys, if you're interested. I'll let you know when I've published that. It's very close to working. There's just like one last bug I'm trying to fix.
Well, it was great that you gave us the inside scoop, the preview. It's pretty impressive work, the amount of work that you've done, and
Thank you.
I think having this in Swift is huge because the Apple ecosystem is, especially with phones and everything, is enormous. So I can definitely see people being interested in either integrating with their own wallets to have Chia Coin basically as part of that, or interacting with that, because there's a lot of wallet apps on the iPhone. So having that, it's going to be, I think, I wouldn't be surprised if you get a lot of interest.
I'm excited. Yeah, and it's a wallet technically, but it's really a full node. So people could be running a full node on their phone, validating every transaction, participating as a peer. So yeah, I'm excited for the potential.
Yeah, and it's really cool that you're using this for almost a different purpose. There's a lot of people that have been using private blockchains, right, or making their own, and that's what you're interested in eventually doing, is like having like I'll call it a fork ChiaLisp. In other words, it's its own blockchain, but it's specialized instead of for transacting necessarily, for running having nodes to run apps on the mesh network, right? And being able to back a long time ago with BBCs, right? It used to be like you'd get time on the thing if you gave them documents that you got from other places. So I'd be like going to different networks, right, and transferring files. Basically, like if you spent the money to do that, they give you time on their network. Like you're like a good user, so they give you extra time, because it'd only be one modem at a time, right? So it'd only be one person connecting. This was back in the 80s, right? And I kind of see this as like a modern version of that, where you you're on a node, right? It's, you want to, one way to instead of accessing the internet just by money, you can also access the internet by contributing to the network itself, right?
Yeah, I'm not expecting to run the entire apps on chain. That would be super expensive. But specifically, what I'm excited about is DIDs, like decentralized identifiers.
I see.
So this kind of solves it can solve the key distribution problem. So if we have an identifier on chain, that's implemented as a coin, and I can just track that coin. And if I want to add a new public key or revoke a previous one, that coin will just make an announcement. And by tracking that coin, I don't have to be directly connected to that person, and it can be totally asynchronous, but I'll receive their announcement in a completely verifiable way. So I think that base layer can be used to build a lot of stuff on top of.
That's cool. So anyone else have any questions for Oliver? And we can also open up the floor too if you have any questions for Luther, or you want Luther to do a demo, or okay, everyone's quiet here. I mean, I want to see a little demo from Luther.
I would definitely like to see a demo.
Hold on a second. I could show some things if, am I speaking?
Yep, we hear you.
Hold on a second. I have to plug in, unplug something.
Cool. No rush.
I could share a different screen, and then you can see. So I've taken the little CPU card and I've plugged it into my computer through the USB UART port. And let me share my screen here for a second. Let's see. Select window or screen. Screen 1. Okay, now I'm doing that. But let's see. Do you see a window there and it says PuTTY inactive?
No, I don't see anything. I still see your camera.
Oh, hold on a moment. All right. Let's see what I'm doing here. Okay, so that's, oh, I needed to select window screen. I have to do that again. Screen 1.
Well, we got a thumbs up on YouTube wanting a demo. Okay, now I can see your screen.
Okay, now let me put this down, and you are sharing your entire screen. Good. Okay, and let me start this, and MakerLisp, open. Okay, good. And I'm going to hit reset here, and here's MakerLisp 1.5. So I can, run this is just a Civ program that's running over and over and over again. And you can see the first time it took a little while to load the program and kind of jit it up and get it going, but that's Civ Veritasthenes. Let's see, what else should I show? Let me go to the demo directory. Let's see, what have I got here? Well, I don't have, let me show you, let's see. Yeah, I don't have anything plugged in or any IO devices plugged in right now. Just want to show that I've got all the IBM PC characters here, so you have the line drawing characters and things like that. Code page 437, ordinary IBM PC character set. You can change the color on of the, so I've got a full ANSI kind of, ANSI attributes and things like that. So it's kind of a normal IBM PC style text display. Here's an outline of an editor, that uses the line drawing characters. And but let me go back to not sharing and just show you a couple of other little IO devices.
Okay.
So in this board behind me, I've got all these little temperature sensors. Let me just show you. So is this little board?
I think your camera off.
Do I have
he's back on his camera though. If you don't see it, it might be your browser.
Okay, let me refresh.
Okay, so here's a little board. You can see you can see I've got the chip in the middle that is the temperature sensor. You see a little bird on there. So,
Yeah, pretty cool.
so this is just a very simple breakout board, but I've got demo programs that allow you to use this, or I've got an SPI version. I've got a couple of I2C versions that that you can play with. What else did I want to show you? I don't have everything kind of like, since everything's kind of behind me and it's hard for me to move the computer around, I don't have a camera that I can point at things. Although, I'm going to attempt this. I'm going to pick up the computer and point it at the board while it's operating.
Let's see. And okay, I lost video. Did you guys lose video?
Yeah, me too.
That's what happens. This is why Apple doesn't do live demos anymore. You notice everything's on video. They had a presentation today. Everything's on video. But we like to play fast and loose here. This is cool. Yeah, and just to remind people, we actually have like a 2-hour presentation that Luther did on it, where he goes into detail of how the machine works and everything, and the whole thought process behind it, as well as we also have if you want to learn more about ChiaLisp, you can also check that out from September. And we're still ongoing for our AI series, so that's still going. You guys have been seeing the video every week. We'll see if Luther comes back. And okay, so if you don't see the demo here, you can see it on there. Okay, actually, we got a question, but I'll see when Luther comes back. I'll ask him. So Oliver, I have a question for you about your presentation. What was the what are the types of places that you plan on needing like other people to help you out with when you do here we go, Luther's back. But let me ask you this, Oliver, first. What parts of your, because it looks like you have a pretty detailed CLVM, but what are the parts that what are the current problems that you're tackling with the project?
So where I am right now, I've gotten to the point where I'm spending coins, and so I need to generate the solution for the coin, and then submit that to the chain. And there's a little bit of a bug. It's running the program, but when it goes to generate those conditions, I don't know if you remember, but it's like the final step. Yeah. It creates those conditions. There's something wrong with the list or whatever. So the first condition is a list, but then the second condition is just appending what should also be in a list as individual items, if that makes sense. So I'm just trying to debug that.
I see.
Once that's working, I think there'll probably be a few more little bugs, but it should be functional. I think at that point I'll probably need to do a bit of optimization. It's a little bit slower, or I think some things are a bit slower than the Python implementation. Just because I've been focused on getting things working and cut some corners.
That makes sense. And Luther, I got a question from you. Okay, obscure answer question. Does it respond to Control T? I think that's right.
Control C, sure.
There you go. That's the answer.
Yeah. I mean, there's a particular bunch of things that are going on in order for that to work, but yeah, basically, Control C causes an exception to happen, and exceptions, fire and then break you out of the evaluation loop. And then if the exception variable is loaded with a continuation, that's the continuation that gets applied to the error message or the error data, which in the case of Control C is actually the $C. So yeah, there's a full exception mechanism in there, and it is used for Control C, but it can be used for other things as well.
I have a question too, actually. So sorry if you mentioned this in the talk, but I remember you said there's no operating system. You're just evaluating the Lisp directly, I believe.
Yeah, I mean, the Lisp implementation is one C program, and the C program is running right there on the processor. There's no operating system. I mean, obviously, I've got a few library functions here and there, and of course, the program itself knows how to deal with I/O devices, but it's not going through, an operating system with a whole bunch of system calls and things like that. It's basically there's one program on the machine, and it's doing everything, and it's got interrupt handlers, but it's all coming straight into the one C program.
Very cool. I guess I'm curious. I think I saw you write ls, and it showed some files. Is that how does that work?
Oh, well, there's a file system primitive function that the ls thing here. Let me see if I can bring that. Well, I'd have to share again. But ls is just a Lisp program that is calling a primitive that knows how to open up the file system and do that. So, I've got the Lisp system proper, but then I've got lots of library functions. So one of them is a fat file system, and it's the Elm fat file system, which is pretty commonly used in a lot of embedded system projects. And so I've got some primitives that are built into the implementation that know how to reach over to that file system. I've also got a foreign function interface so that you can link the basic software against any other C library you want. And there are functions that move C types to Lisp types and back and forth. So those C standard library functions can show up and look like Lisp functions. And, a string in C turns into a symbol in Lisp, and an integer in C turns into an integer in Lisp, and a double in C turns into a double in Lisp, and those kinds of things. So I've got a couple of ways to bind this together with other programs. But yeah, so there's the Lisp system proper. There's the Zilog supplied low-level routines for accessing keyboard and interrupt and things like that. Library routines. There's the fat file system stuff, and what else have I got in there? That's pretty much it. And then, of course, code that I've written to deal with the vagaries of the Zilog machine itself. So, but it's like a monolithic embedded, embedded, program. Not counting on a lot of, it's not running under a real-time operating system. It's not running under a larger operating system. It's not doing any scheduling or anything like that. It's the Lisp implementation is itself deciding what happens when.
That's super cool.
Thanks.
I have some questions on what's it called, the Core 24.
Yeah.
So I was curious, did you base the core off of some previously existing FPGA core?
No, I've read a bunch of those for ideas and for understanding of how people do things. And, I've never done something exactly like this myself. So I'm learning as I'm going, but I'm building it from the ground up. So, right now I have a basic, kind of state machine, and I've got a simple program that can do hello world that's almost running right now. And I'm taking that and dropping it into some example programs that have been made for these other little FPGA evaluation boards that do demonstrations. So I'm kind of hollowing out those sample projects for example, let me see. Here's a little FPGA evaluation board, and it runs, it's a Lattice, FPGA, and it runs Lattice's MICO 8 processor, soft processor on this FPGA with a UART and with a bunch of other peripherals. And I'm developing my CPU core apart from that, but I'm going to drop my CPU core into the kind of the fabric of the UART support and things like this in here, and then run my program, not the MICO 8 program. So I'm kind of learning as I'm going, it's a challenge, by the way, to just keep the frequency up, and so because I'm doing things a little differently. It's not, for example, it's not going to be a pipelined, RISC-like implementation, because it's not like a RISC machine that has a standard fixed size instruction, and it doesn't have an instruction encoding really. The instructions are simply, the first byte tells you everything that you need to know, and it's just an enumeration of all possible instructions. In this computer, there are only 3 general purpose registers, and there's a frame pointer and a stack pointer, and the instruction types they're variable length, but basically the opcode, the first byte, tells you everything. It is like, so for example, I don't have fields in the instruction that says this register and this addressing mode and things like that. There's not a fixed encoding like that. And so in the interpretation in the microsequencer or the microarchitecture of instruction execution, you don't go look for fields in instructions and then route them to ALUs and things like that. Instead, I've got one giant state machine that's indexing off of the opcode byte and another few bits for the stage that you're in. And it's just like one big state machine. And then so for example, I've got about 170 instructions defined right now. But like instruction 4 tells you everything you need to know, which registers you're using and whether it's a load or a store and things like that. So instead of having a decoding phase, I just index off the opcode, and then that takes me to the particular state that does the particular things that it wants to be doing. And I'm doing it that way for a couple of reasons, but mainly for code compactness. But instruction fetches, it's not pipelined in that sense, but instruction fetches are overlapped with instruction execution. So it's pipelined in that way. And basically the execution time relates to how many bytes there are to fetch in the instruction. So the way this thing runs, there's one 8-bit port to memory. And the EZ80 is like that too. And so as long as I'm keeping that port busy, I'm either doing a memory fetch for data or I'm doing an instruction fetch. And as long as that is busy, then that really dictates the rate at which that you can execute. And so for example, in the little sample program I've got right now, I've got 6 instructions implemented that take 18 clocks to do 15 bytes worth of instruction. And the extra bits are because there's a couple of delay stages in the memory fetch. But I'm getting there. It's going to take me a little while, but it's in Verilog, and I'm kind of doing it from the ground up. Although I am definitely reading other people's implementations.
I'm kind of curious if you've thought about doing any sort of Lisp-specific kind of instructions in the past, or in the spirit of, say, a Lisp machine.
Yeah, I get that question a bunch. No, no, not really, not really. I have found that general purpose computers have just about everything you need if you've oriented your implementation, to be good for general purpose computers. So sometimes it seems like tagging data structures, would save you a little bit, but the encoding scheme for pairs and for atoms that I've used makes it pretty simple, and I've stuck with that. So although I know people have done that in the past, I don't see that it really helps all that much. So no, the only thing I really want is I want access to a lot of memory as efficiently as possible. And one of the things about this processor, which is like the older processors and what I liked about this embedded processor, there are no levels of memory hierarchy. So that does influence my design in a certain way, because I want it to be a simple system, and I don't want there to be caches or virtual memory or anything like that, which means that I want the frequency of the internal core to be as high as possible, because when I do access memory, I'm going to, have to slow down to the speed of the memory, but that doesn't mean that I can't be running internally as fast as possible. I don't have a lot of registers, so I can't go that long without touching memory. But on the other hand, the FPGA has internal memory, which I'm not using as a cache, but which I can put code there, and I can put stack data there. And so I plan on doing it that way. So there will not be really memory hierarchy, but in a cache or virtual memory sense. But I will allow those resources that are built in on the FPGA to be accessed by the customer. So you can put you will be able to put tags in the C compiler on a routine, and just like in embedded system programming, you'd say this is an interrupt routine, or I want this to be in Flash, or I want this to be in RAM. You will be able to allocate certain small amount of code to be running in the internal memory, which will run 3 times faster than the system memory. So I'll do it kind of that way, sort of by hand, And so the Lisp system being the one application that's running on this thing, of course, I'll do the same thing. I'll just in the same way that I rewrote some of the C code in assembly language because it was important to the application, I'll take some of the lower level important stuff and have it being run in the, precious, fast, embedded RAM inside the FPGA, and not have to go out to main system memory. So, so it'll be like that, kind of.
Can you simulate threads with interrupts and continuations?
Say that again?
Can you have threads with using interrupts and...
In fact, I've got a demo that shows that. Yeah, in fact, I could show you that demo, or let me bring it up on screen. That would probably be the easier way to see it. Let me first find it over here on my Linux system. Yes, I have a demonstration where I use continuations. I have 2 things in a coroutine relationship, and they're calling back and forth in order to bounce back and forth. And you can run the demo, and it shows the transfer of control going back and forth. So let me find that.
Okay. while you do that, actually, I have a quick question here from YouTube. Does the I think this is directed to you, Luther. Does the JIT operate from source or pre-tokenized form?
From source, well, it's hard to say. It's like source, but it's already been, the expressions have been read, so they're in their in-memory form. So they're Lisp lists and atoms at this point. So they're not symbols and characters in ASCII anymore. Well, of course, when you're, read, evaluate, print, right? So Lisp loop is reading things from the reader, and it's being converted into an in-memory form, and now you have your program as Lisp data structures, and those are the things that get broken apart and reduced down to virtual SECD virtual machine instructions. So there is no ASCII text left at the point where you're starting to break these things apart. That's happened as the expression got read in.
Okay. Hopefully that answered that question. Yeah, now you can continue on with Mike's question.
Yeah, I'm looking here to find it. I will find it in a moment. It's not in the demo directory. It's in my test directory. Hold on a second. Source Lisp Linux tests. Okay, what I'm going to do is I'm going to share my screen again and show it to you on the Linux system. Hold on a second. Select window or screen to allow. Okay, let me make this a little bigger. Let me make this bigger. And then, okay, so can you see this? Do I need to make it bigger or something? Or can you see it?
I don't see your screen, but I might need to reload.
All right, hold on. Maybe you refresh, and meanwhile, let's see. Let's see. I need to disable my camera, or let's see. Let me make
now I
that
can see.
big. Can you see the screen now?
Yeah.
Okay, maybe I should make the font bigger or something like that. Or maybe I can, I wonder if I can. Can you read those characters?
Yeah, everything except for the cyan, but I think I can figure out what those are.
Oh, I can.
I think it says like lambda and let's, but yeah, I can read it.
Oh, yeah. Okay, so, the comment says test coroutines using continuations. And you can see I've defined a resume macro, which basically just, when you do a call with current continuation, what you get is, you call with a continuation there, and then that thing's returning the continuation, and then I'm setting it, to that variable. So when you do resume T2, basically you're, I come into task one, right? And I say, let, T2 equal task two. And that basically is that task two function. And then I'm printing some information there. And when I do resume T2, what that's doing, it's calling, with current continuation task 2, but you can see that task 1 and task 2 take one argument, which is the continuation, because that's the way you use call with current continuation. And what will come back is, I'm assigning, the continuation to T1, and then when I do resume T1, for example, in task 2, you can see what I'm really doing is I'm calling with current continuation that continuation. So I'm returning back to the same place where task 1 had left. So I'm using continuations to go back and forth here. So, you run a little bit, and when you do the resume, you're suspending yourself and resuming back at the point that you were last in the other task. Do you see that?
Yeah. I guess what I was wondering is, let's say you have a timer interrupt. Can the timer interrupt get delivered the current continuation, what was executing, and then resume a different continuation?
Well, it could if I had timer interrupts hooked up that way. You can do that with Control-C because I have Control-C hooked up that way, but I don't have any other system interrupts currently hooked up through this system. So, for example, in the Lisp interpreter, I know what a Control-C event from the keyboard handler looks like, and I can determine it. And then I can use that to throw an exception. I don't have any other system interrupts or timers set up that way inside the Lisp system to be recognized and then, call a particular exception. But I could. So if you would like to see that in an upcoming version and a demo that demonstrated that, I can do that. I don't have any timer interrupts happening in the system at the moment. I have. Go ahead.
So the Control-C interrupt, can it get the continuation that it interrupted to resume?
Well, yes, of course, because
Okay.
what you do is you can actually set what the exception handler will be. And so you can create your own code for that exception handler, and that exception handler could then call that continuation if you want, or anything else you want. So there's a default, if you don't, there's a magic variable called, the exception handler, like asterisk exception dash handler asterisk. And that's a special variable it's not special really at all. It just, I made it have a special, like funky looking name so that it wouldn't get commonly used by everybody else's variables. But it is also special in that the implementation knows about it. And so what happens is when an exception happens, and there's various things that in the implementation that can cause an exception, and Control-C is one of them. But when an exception happens, the evaluator, the evaluation loop looks and sees if this magic variable has defined anything. And if it isn't, it just does its default, bounces out to the top and you're back at the top of the interpreter loop. But if something is there, and if that variable is loaded with a continuation, then it calls that continuation, applies that continuation to the error result, which, calling it. And then that'll resume or do whatever that continuation will do. So I've got other examples where I'm setting the continuation, the exception variable, so that we can pop out and do a particular kind of error handling. But you can put anything you want in there. So, and Control-C is one of those. So yes, you can have your own Control-C handler, and make it return to some other code or make it do anything else.
But can that handler get the continuation that it interrupted?
Well, you have to put that can it get the continuation that it
So,
interrupts?
so like, let's say you're running an ordinary Lisp program and it's doing its thing, and
Mhm.
the control C, the exception handler wants to do what it does, but then have the continuation that will resume from before the
Oh, yeah.
interrupt happened.
Oh, yes, it can definitely go right back to where it came from.
Okay, cool.
Or it can do something else, whatever you want it to do. So, yes, it can return. I mean, basically, if it does return, it'll just come back to where it came from. Let me, I'm having trouble like making my system do what it's supposed to do. Hold on a second. Oh, because I'm looking at my shared screen. That's wrong. I need to go, I'm kind of caught in an infinite loop here, looking at myself.
So if you capture you can capture the current continuation in your interrupt routine, shove it off somewhere, and then later when that continuation is invoked, you'd go back to where you were when you were interrupted.
Well, yeah, I don't really have interrupt routines in the Lisp system right now. All I have is I have exceptions, and the only thing that is hooked up to an exception is the Control C. So if I were going to do more interrupt support, I would make other types of interrupts be able to behave like Control C. And then they could either go to the one exception routine, or they could go to their own exception routines, which would be other magic variables. So why is this? I'm trying to get out of, there we go. Finally. Okay. Now I can see everybody again. So, yeah, let me, you guys keep talking, but meanwhile, I'm going to look for another example that demonstrates the exception handling a little bit better.
I'm reading Lisp in small pieces, and
I've read that.
Yeah, I'm on the continuations chapter, so I'm kind of interested.
Yeah, continuations are great. Or the continuation, as some people say, because the whole stack of frames is the entire history of the state of where you are in the program. So sometimes people call it the continuation. But yeah, it is kind of neat stuff. I'm going to look for another example here that is a little bit more instructive.
Call CC is one of those things that I feel like I understand, but I don't get, if that makes sense.
Yeah, it's a lot. I have found that a lot of these things are hard to understand abstractly, but when you then look at the concrete mechanics of what's going on in the implementation and look at it from the underside too, then you can kind of put it together and it makes it a little easier to understand.
Yeah, it probably doesn't help that not only have I never implemented it, I've never even used it in any sort of real way. And even the toy examples I've tried are very, very small.
Yeah, I have to concur with that. I've mostly used it for, breaking out early in a computation. Like if I want to do something where I want to like return,
but they don't go back in.
A simple thing, yeah. I've tried it for some. I tried to build a yield generate type structure, but I kept blowing up my machine, and I didn't know what I was doing wrong. So maybe delimited continuations might be a little easier than the continuations in Scheme. At least you would prevent something like that.
Yeah, I don't know. I think that I think they're pretty simple, but it's I'm trying to find a better example of error handling. Let's see.
Well, I'm getting to understand continuations, but delimited continuations completely confuse me.
I mean, essentially, you could think of regular continuations as being delimited by the entire program, and in delimited continuations, you can actually put a mark, so it only goes. You can only return to that mark, and you don't save everything. You don't save the whole stack, basically. At least that's my understanding.
What's the purpose, though? Why do people want to do that? Have they got a portion of the environment on the stack, or what's going on?
I think I think it makes certain uses of continuations easier, and more efficient. While at the same time, you can still, if you really want to, I mean, if you set your mark at the start of the program, then you still have regular continuations. There's a whole paper about this. I forgot the guy's last name, but where he talks about the problem with continuations, or why we should be using delimited continuations, which I read a few years ago, but right now I have amnesia, so I don't remember what his reasons were exactly, but they seem pretty legit to me. You know. But yeah, I think continuations, at least for me, were the hardest things to reason about in Scheme, and I kind of tend to avoid them, except for the most simplest things. Like I said, like escaping early is a common thing. I don't know why, but when I write programs with continuations, I get lost. I'm like, what? Okay, what is this doing? Okay, now it's going over here. Where did it come from? I don't know. That could be me, though.
Okay, I've got an example that I can show a little bit. I've got a second level. First of all, the other thing I'll say is that I use closures and continuations and macros to do all these different kinds of forms, like while and for and things like that. I mean, you really need them in order to do things like loops and things like that. So it's you can have an inner loop and an outer loop, and I can go into that. But I have an error handling example here. So let's see. I guess I have to share again. Okay. Okay, so I've got another, let me take a look at that, see if it's visible. All right, so I've got another program here. What this is a second level. Let me put this other thing down that's kind of distracting.
Also, if you can make the text a little bit bigger.
Yeah, let's see. I don't know.
What is call CE?
Well, that's a macro that I created myself, and it's like call CC, but I've done something a little different so that. Okay, let me find it. It's something where I've done something a little different for this particular program. Let's see.
What does just CE mean?
The current environment.
Oh,
So,
okay.
so I here it is. What I've done you see this call CC with a guaranteed new continuation of the current environment. So what I'm doing is I'm doing call CC, but I'm guaranteeing that I'm creating a new continuation. So you know, if you don't necessarily, you know, because of tail call, tail call optimization, if something is the last call in an expression, it's not going to push a new continuation before you call that thing, because since it's the last thing and when it returns, you're going to want to pop that one off and then return from that. It doesn't push a continuation. But in this one here, I'm forcing pushing a continuation because it's something that's going to hold the environment. And so for this example, I needed it.
Okay.
Did you get all that?
Yeah,
You know,
yeah, yeah.
Yeah. So I'm keeping the tail call optimization from preventing a continuation being created, because I'm going to need that continuation because I don't want to hang on to it and do stuff with it. So that's what my call CE macro is. It's like call
Okay.
CC, but
Okay.
doesn't get to it. All right. So where was I? Okay. I don't know how to make the font bigger. Hold on a second.
I can read it okay.
You can read it okay? All right. Fine. So
unless you've messed with your hotkeys, Control X, Control Plus, I think should make it bigger. If you're looking at it with an Emacs.
I am in Emacs. Let's Control X, Control Plus. No, it doesn't do it. It gives me that little error message at the bottom. Didn't like that.
Oh, do you have Emacs open from within a terminal?
No. This is within terminal, yes.
Oh, okay. That's probably, yeah, that's different in that context.
I can go to like the regular Emacs. This REPL. Control X, Control Plus. Now, yeah, Control X, Control. No, didn't like it. Anyhow, maybe these characters are a little bigger. So, anyhow, I've got a second level REPL here, and I'm looping until the end of input. But you see this error continue here? This is like the magic error handler holder of continuations. And this global macro affects creating this as a variable at the top level. Okay. So it's global. There's no thing in the language called global, right? I'm just doing a set Q. But what I've done is the global macro captures the top continuation at the time where you're at the top level in the environment, and I capture that, and then the global macro does an evaluation of set Q with that continuation. One of the things I can do in this Lisp is that I don't allow you to create environments and pass around environments like some Lisps do, but you can capture an environment through a continuation. So if you capture the continuation, you can supply the continuation as an argument to eval, which means that when you do an evaluation of the expression, it gets evaluated in that environment specified in that continuation, and therefore using that, the global macro actually can allow, wherever you are, you can set something in some other environment. And so what I'm doing here, the error continue variable, I always want it to be defined at the top level of the environment. And so I use that's what's going on here. So I come in to get expression, and this variable defer actually stops control C's for a little while. And you get the df variable is taking the value of what defer returns, which is whether it was deferred or not already. And then, so I'm stopping control C's from happening because I don't want this to get interrupted right here while I'm changing the error handler. And then I take this continuation that is the current continuation that came in when I called with get expression, and I'm setting the current continuation to be the error handler. So, and now I allow control C's to happen. Now I'm going ahead and I'm doing reading and stuff like this. But what happens while I'm doing a read, if the read throws an exception, it's going to come back right here, to this, to what is the current continuation, which means it's going to bounce out to this place right here. Okay, so here in my continuing, loop here, while is also a macro that's doing all sorts of stuff to make it look like while. I'm doing if set QE, the result of the get expression is either going to be, not an error or an error. I'm calling get expression with call CC, which means that get expression is past the current continuation, which comes in here. I set the current continuation to be the value of this error continue. Should anything happen in the system when I'm doing this read, it's going to call the continuation in error continue, which means it's going to pop right back here, and that's going to be the value of E. So that's how I catch errors that are happening that way. And then, of course, if there is an error, then I'll show it. But if it doesn't, then I continue.
So control C executes the continuation in the global error.
That's right. Well,
okay.
What happens is, yeah. So I'll just say it a little. What you said is right. I'll just say it in a little bit more detail. The interrupt the character interrupt handler knows to recognize control C as a special character. What it does when it does that is it calls this hook. That hook is in the Lisp interpreter, and the Lisp interpreter says, oh, somebody called the control C hook. That's a control C exception. Oh, because it's control C exception, and if it's not deferred at the moment, that means I want to throw an exception out of the evaluation. Then that pops to the outer level of the evaluation loop, and it says, is the error continue filled? If the error continue is not filled, I'm just going to do the default thing and pop all the way back out the top. But if the error continue is filled, and if it's filled with a continuation, well, then I'm going to affect calling that continuation. And so that is how, because I set it here, and I set it with what got passed in, which was the thing that got passed in when I called here, that means it returns to this point right here. And the value of that the continuation is applied to the error value. And what that means in the case of control C is that this variable E now has quote caret capital C, and that is what gets printed out. Okay, so or control D or things like that. But when it's a control C, that's what it'll have in it. And so that's what happens. So I do the same trick in various other places. Here in evaluate, I'm doing the same trick. Now I'm temporarily setting the error handler to this continuation because I want to bounce back in a controlled way should anything happen, in the process of evaluating this expression. So, and notice I'm evaluating the expression, but I'm evaluating it with krepl, which is actually the environment in which I want, which is the continuation that I captured for the environment in which I want to evaluate this expression. So let's see if I can find that. Where did I call evaluate? Call CC. Evaluate.
It's right at the bottom where you call CE_REPL.
That's true. And where did I set krepl?
At the top where you define _REPL.
There you go. That's right. So this clearly shows that right here, this place is the environment within which I actually want to evaluate this expression. And so that's how I do that. So you're right. And the reason I did call CE here is because in various different versions of this program, this call wound up in different places, and sometimes it was creating a continuation and not. And so what was happening was, instead of it being evaluated in this environment, it was being evaluated in the environment of the caller of this thing, and it was causing trouble. So I made this macro to just guarantee I had pushed a continuation that corresponds to this environment right here. So,
and if error continue has just a function that doesn't muck with anything and just returns, it'll continue from the interrupt point.
Well, error continue has to have a continuation. Otherwise, it is ignored, and then it'll pop out to the default. So the evaluation loop expects a continuation there, but of course you can place that continuation anywhere you want, but you will have to create a continuation with some variant of call CC. So it doesn't take multiple different types of values in error continue. It wants a continuation to be there because it's going to apply that continuation to the error value, and then it expects that to be the return value at wherever that continuation returns you to.
Well, thank you. This is helpful, but I'm afraid I have to say I think my brain is my Stack Overflow.
Yeah, it's a little mind-bending and various aspects, but send me email at luther@makerlisp.com and we can have a continued discussion, because this stuff is really interesting and fun.
You're telling
you can also
me I should grab my current continuation and send it to your email. Funny.
What do you think?
So you're telling me I should grab my current continuation and then call it with your email address. I'm making a continuation pun.
Yeah, okay. We can continue the conversation at the point at which we had accepted out. So
there was actually a comment, L user Droog. He wrote, the old MIT paper, Cheney on the MTA, discusses implementing continuations in non-standard K and RC. And then he had arrows and says, completely insane usage of alloc.
Oh, yeah. Well, I
think I need to read about this because I've never heard of it before.
Well, I mean, I can
like
imagine.
An story.
I haven't read that one, but I can kind of guess what it might be doing. But everything in the implementation is using the same heap and the same garbage collection, the same Lisp data as everything else. So every time I need to do something like that inside the implementation, I'm using the same store that the rest of the Lisp program that's actually the Lisp program that's actually executing is using too. So everything uses the same kind of data.
Mhm.
So when I need something, I use the same stuff. Everything's garbage collected and garbage. I do garbage collection a little different, but that's kind of a long story too. But it's basically a chainy copying collector with a couple of twists. So I'm going to stop sharing now.
Okay. I'm gonna just quickly check on YouTube if there's any other questions. We'll see if anything pops up for a second. Okay. Well, I could tell you this was a fantastic discussion. Thank you very much, Luther and Owen. Oliver. Sorry. Sorry.
Hey, Oliver.
Oliver. Yeah, thank you guys both. I want to thank everyone on YouTube. Keep checking out our videos, and we're going to close the parentheses on the live stream. We're going to hang out a few more minutes, but I guess we'll see you next time. So with that, let me turn this off. Okay.